When nitrogen dioxide is exposed to sunlight, it falls apart to produce nitrogen oxide and oxygen atoms. This is a decomposition reaction that is one of several that help to produce photochemical smog, a major problem for human health in urban areas. Let's say we are interested in studying how rapidly this reaction takes place. This is also known as studying the rate of reaction. To do this quantitatively, we must measure the change in the reactant or product concentrations as time goes forward. After measuring these quantities, we use the data to calculate a numerical rate of reaction. Before doing this, it might be good to think generally about what we expect to happen to the concentrations as this reaction takes place. Because nitrogen dioxide is a reactant, its concentration will begin at some initial value and then decrease as time increases because reactant concentrations go down as reactions go forward. Note that the concentration approaches zero as time increases, indicating that all of it is being consumed. The concentrations of the products, nitrogen oxide and oxygen atoms, begin at zero because they do not exist at the beginning of the reaction. Their concentrations will then increase as time increases because they are products and they are formed as the reaction goes forward. The concentration of each of the products approaches the initial concentration of the reactant, indicating that the reactant is being turned into products, each with the same stoichiometric coefficient as the reactant. Let's look at how rapidly this reaction takes place by examining the rate of change of the concentration of the nitrogen oxide product. We are free to measure the concentration change of any reactant or product, but we'll start with nitrogen oxide. To do this, we pick some time during the reaction, called T1, and record the concentration of nitrogen oxide at that time. We give this concentration of NO at time 1 a label with a subscript 1 to indicate that it is the concentration at time 1. We then pick a second time called T2 and record the concentration of nitrogen oxide at that time. We give this concentration of NO at time 2 a label with subscript 2. To compute the rate of reaction, we take the difference between these numbers, second concentration minus the first concentration, and divide by the difference in time, T2 minus T1. This is the rate of reaction during this time interval. We can express this more compactly if we use a special symbol to indicate the difference between the final quantities and the initial quantities. That special symbol is the capital Greek letter delta, and it always means change in whatever comes after it, which is always defined as the final value of that quantity minus the initial value of that quantity. This allows us to express the rate of reaction as delta concentration of NO divided by delta T. This is read as change in concentration of nitrogen oxide divided by the change in time. It is worth pointing out that this is a positive quantity because the second concentration is larger than the first concentration and the change in time is always positive as well. This is how the rate of this reaction is expressed in terms of the change in concentration of the product, nitrogen oxide. This seems fairly straightforward, but this is not the whole story. Let's look at the same reaction of nitrogen dioxide decomposing into nitrogen oxide and oxygen atoms when exposed to light. We have already seen how the concentration of the reactant in products change in time, and we have determined that the rate of the reaction is the change in nitrogen oxide concentration divided by the change in time. Because both nitrogen oxide and oxygen atoms have the same stoichiometric coefficient in front of them in the balanced equation, which is 1, we could have measured the oxygen atom concentration instead, which would have given us a rate equal to the change in oxygen atom concentration divided by the change in time. Both quantities are the same and both are the rate of reaction. It is worth pointing out again that this quantity is positive because product concentrations increase as time increases. What if instead we want to write the rate of reaction in terms of the change in reactant concentration? To do this, we do what we did before. We pick two times during the reaction, T1 and T2, and measure the concentration of nitrogen dioxide at T1, which we call concentration of NO2 sub 1, and at T2, which we call concentration of NO2 sub 2. The rate of reaction is the second concentration minus the first, which is final minus initial, divided by the time difference, T2 minus T1. In shorthand, this is delta NO2 concentration divided by delta T. But there's a problem with this. The second NO2 concentration is always less than the first concentration because reactant concentrations decrease as time increases. This means that the change in concentration of NO2 is negative, which in turn means that the rate of reaction computed using reactant concentrations is negative. This is not what happened when we computed the rate of reaction using product concentrations. Does the reaction have two rates? The answer is no. Reactions can only have one rate of reaction, and by convention it is always positive. Because of this, expressing the rate of reaction in terms of the change in concentration of a reactant requires a negative sign. In our expression for the rate, we need to insert a negative sign before each of the terms containing a change in concentration of reactant. The expression for rate of reaction now becomes delta NO concentration over delta T equals delta oxygen atom concentration over delta T equals equals negative delta NO2 concentration over delta T. These quantities separated by equal signs all have the same value. We always have to remember that a negative sign must be placed in front of the terms that use changes in reactant concentrations because reactant concentrations decrease as time increases. This is called a rate expression. It relates the rate of a reaction to the change in concentration of all the reactants and products. We'll use this a lot. Let's see if we can apply this new knowledge. For the same reaction we've been considering, what is the rate of change of the nitrogen dioxide concentration when the concentration of nitrogen oxide is increasing at a rate of 0.26 molar per second? To answer questions like this, you should always write a complete rate expression. The rate of reaction is the change in concentration of NO divided by the change in time. It is also equal to the change in oxygen atom concentration divided by the change in time. Finally, rate is also equal to the negative of the change in concentration of nitrogen dioxide divided by delta T. Remember that the negative sign is there because NO2 is a reactant. The problem tells us that the concentration of NO is increasing at a rate of 0.26 molar per second. This is the value of delta NO concentration divided by the change in time. So we can go ahead and plug this value into the rate expression. This gives rate of reaction equal to 0.26 molar per second equal to delta oxygen atom concentration divided by delta T equal to negative delta NO2 concentration divided by delta T. The question asks us to find the rate of change of the NO2 concentration. The rate of change of the NO2 concentration is delta NO2 concentration divided by delta T, which is a part of the last term of the rate expression. All we have to do is solve for it. Because all these terms in the rate expression are equal to each other, we can pull out just the two terms we are interested in, giving 0.26 molar per second equal to negative delta NO2 concentration divided by delta T. To solve for the rate of change of NO2 concentration, we multiply both sides by -1. This gives negative 0.26 molar per second equal to delta NO2 concentration divided by delta T. The answer to the question is therefore negative 0.26 molar per second. The negative indicates that the nitrogen dioxide is decreasing in concentration, which is expected because it's a reactant. There's a related question we could ask and answer. What is the rate of disappearance of NO2 under these same conditions? Using the word disappearance implies the negative because to disappear means to decrease. Therefore, the rate of disappearance of a reactant is always the negative of the rate of change of the reactant concentration. Thus, the rate of disappearance of NO2 is positive 0.26 molar per second. Mathematically, the rate of change of the NO2 concentration is delta NO2 over delta T, and the rate of disappearance of NO2 is negative delta NO2 concentration divided by the change in time. Terminology like this is going to be important, so let's see if we can clarify it a bit. For the light-induced decomposition of nitrogen dioxide, we have already written the rate expression several times. We have worked an example in which we solve for the rate of change of the reactant concentration, which is delta NO2 concentration divided by the change in time. For a reactant, this will always be negative. We can also solve for the rate of disappearance of the reactant, which is the negative of delta NO2 concentration divided by the change in time. This will always be a positive quantity. The word disappearance implies the negative. We have also talked about the rate of change of the product concentrations for nitrogen oxide and oxygen atoms. Mathematically, these are delta NO concentration divided by the change in time and delta oxygen atom concentration divided by time. These rates are also referred to as the rate of appearance of the NO and the rate of appearance of oxygen atoms. Mathematically, these are the same as the rate of change for that product. For a reactant, the rate of disappearance means the negative of the rate of change of that reactant. For a product, the rate of appearance is the same as the rate of change for that product. It makes no sense to talk about the rate of disappearance of a product or the rate of appearance of a reactant, so you'll never have to worry about that terminology. And that's Introduction to Rate Expressions.